G'day, my name is Brendan. Thank you for attending this talk. It's really great to be here at FISL in Brazil. I've had a good time so far. This is my first trip to Brazil, and I've discovered that the soft drink tastes similar to the soft drink from Australia, my home country, although now I'm living in the US, so it's been fun. And I've seen a lot of great talks so far this week on open source. My talk is about performance analysis and a new methodology, the use method that I have developed. And I will talk about open source occasionally because it is quite relevant. Some of the broader points about open source have already been made previously through many of the really good talks that I've seen this week. But there will be some new things that I'll be adding during this talk. I work at the top of the performance chain at the moment, so I deal with the hardest of performance issues. I also write open source performance tools out of necessity to solve issues. These are often done because I have a customer issue that I need to solve, and I'm working as quick as I can to solve it, and the tools don't exist. I share them on github.com on my homepage. I also write books. I co-authored a book on dtrace, dynamic tracing, and also Solaris performance and tools. I am known from my work at Sun Microsystems, Oracle, and I now work for a company called Giant. And just to briefly mention what Giant is a cloud computing provider. We also develop cloud computing software. We have an operating system called SmartOS, which is based on the illumos kernel, and illumos in turn is based on Open Solaris. We also run Linux and Windows. So nowadays it's really exciting. I get to work on performance issues on Linux and Windows and SmartOS, and get to see all sorts of interesting things on the cloud, a lot of very difficult issues. So for the agenda, I'm going to begin with an example problem so that we can see how methodologies are useful on something concrete to think about. I will then talk about 4 different performance methodologies. In particular, the use method. That will be the focus of the talk. And I will finish with some specific tools on how these methodologies can be applied. So for an example problem, sometimes it's hard to include example problems in my talks. I like to bring them from the real world, but the real world is often gritty and complicated, and it's hard to find a clean, small example to make a point. So this isn't a clean, small example, but this is a real example, and so that's why I've included it. This actually happened very recently. A customer reported a performance problem with a database. They said the database response time sometimes takes multiple seconds. Is the network dropping packets? Yeah, this sounds like blaming the network. However, the customer did test it using traceroute, which showed that there were some packet drops. That was the problem statement. We have a database. Sometimes it takes multiple seconds to respond to queries. Think about how you would approach this problem. What methodologies, where would you begin to look? The customer has said it's network packet drops. So would you begin to look at things involving the network? This is what happened. So I've drawn a very simple diagram of the support pyramid. So we have first level support, we have second level support, and we have people who act at these levels, and we have top of the support chain. The customer had said there were network drops. At the first level, they ran traceroute from the problem description, and they couldn't reproduce it. At the second level, they looked at the network and did forensics on the system statistics, and said the network looks okay, and talked to the networking guys as well that run the routers and switches. Networking does actually look fine. The second level support also checked out CPUs. CPUs weren't part of the performance problem description, but it was a good idea, and the second level support said the CPUs look okay as well. So you can see they're following their own little methodology. Let's check something else while we're here. So then it was my turn. So I have first level can't reproduce it. Second level says it looks okay, and we've really checked the network, but the customer still has the issue, and they've seen network drops. So there is an old-fashioned way to do this, and that's to use network packet sniffing. You can do that via tools such as TCP dump or snoop. There is performance overhead during capture. So the CPU code paths to collect the data, and also to store the data, and then to post-process that. Again, there's more CPU involved there. How do you actually do this? So you run TCP dump do you run it for 10 seconds or 10 minutes? I asked the customer, how frequently is this problem happening? And they said, about once every 10 minutes. Okay. We're on a 10 gigabit production network. Do I TCP dump for 10 minutes, let's say 15 minutes to be sure, and then capture that, and then post-process that? So if you crunch the numbers, this could be something like 1 terabyte of data that I'll capture. Then I might be moving that from the system to my desktop, so I can run Wireshark on it, or run other tools on that. So there is a lot of overhead to do this. In fact, moving that 1 terabyte itself will be causing issues on the production server because I'm making the network port busy. It's time consuming. This is not real time. It's still commonly done, but there is a new way to do this, and that's dynamic tracing. The first implementation of that was dtrace, which is still the most useful and widespread form. Dynamic tracing is efficient. In this case, I can use dynamic tracing to instrument just the drop and retransmit paths in the kernel, because I'm trying to look at network drops. So let's just look at them. Instead of tracing every send and receive, like TCP dump might be doing, which you can be doing over 1 million packets a second, let's just trace the kernel code paths for when bad things happen. The kernel can drop packets. The kernel can retransmit packets. They don't happen as often as send and receive. And so the performance overhead to trace them is much, much lower. I feel comfortable doing this on production servers, and we'll leave them running in perpetuity, leave that tracing instrumentation enabled. I will not do that for send receive. It's too much overhead. Another advantage is you have kernel status readable. When you're looking at the TCP dump or sniffing packets, all the information has to come from the packet headers. When I'm using tracing to look inside the kernel, I have full kernel context. I can see the TCP state, I can look at all sorts of counters, there are all sorts of structures that the kernel maintains, so it can calculate when to do the TCP sliding window and round trip times. There's all sorts of interesting information that can add to just the packets. It can also be real time. I can analyze this as it happens. So there's an example tool I wrote called TCP listen drop. And what that guy does is when you fire too many packets, too many TCP SYNs at a listening port, when the backlog fills up, the kernel will drop packets. And so this is why we tune the TCP backlog. This tool just instruments the kernel code path that drops the packets, so that I can see who is the source IP, what is the port, what's the destination IP, and what's the time, so I can look at the rate. So instead of tracing everything, I can just go and trace that event. And if that happens, I can tell the customer, either you need to tune the backlog, or you just have too much load for that system. So that's a lot of what we're doing these days. This still does take a bit of time. So for methodology, I did not start with the network drop analysis. I began with a methodology called use method, which I'll go through, which I used to check system health. Now at this point, I have a lot of people interested in the issue. We have first and second level support, the customer has complained, and the salespeople telling me you really need to fix this. But I'm taking a step back and saying, no, I'm actually going to go and do I'm going to follow a methodology so I can check other things, to see if other things may be the issue. In 5 minutes I found CPU was fine, network was fine whilst I was watching, there's only very light usage. Memory was exhausted, the system was paging, the system was out of memory. When your system's out of memory, instead of going to DRAM, which is very fast, you go to disk, which is very slow, many orders of magnitude slower. And this is a straightforward problem for system administrators to go and fix. Go and configure the application. Don't exhaust the system memory. No one had found it because they had target fixation on network packet drops, and were looking at them. Now that's not to say that might be the issue. I shouldn't stop there, I should keep looking. One of the common things that I encounter is there's often not one performance issue, but there are many performance issues. And then it becomes quantifying those issues so you know which one actually is the worst. I also check disks. This following the methodology I'll go through. The disks had periodic bursts of 100% utilization. Doesn't necessarily mean an issue, but it's another interesting indicator that can be investigated. So, by following the methodology, it's simple and fast, and it directs further analysis. And this is something that the first level and second level support and the customer could have followed themselves. When I told the customer what I found, they were surprised. Are you sure? I used latency analysis to confirm the issue. Now, I've included this in the example because it shows there are other methodologies. Really, there are multiple methodologies used depending on the part of the investigation, the timing, and the target. Latency analysis for memory, I won't go through all the details, but I've included it in the slides. For memory, I used microstate accounting. Linux has something similar called delay accounting, where I could prove that the application was waiting on anonymous page-ins because it had been paged out. And then I also used dynamic tracing for that. Dynamic tracing again for disk, and was able to show that disks often happen very asynchronously to the application. This is what file systems do, because disks are slow. And by using dynamic tracing, I could instrument higher in the stack at the application interface and show that this actually was hurting the application. So the application was getting blocked whilst it was doing fsync calls that were taking up to 1,000 milliseconds. And I can instrument the application and show this is also blocking during a query. And so you can prove it beyond a doubt that yes, this actually was the disk. Usually when I do this exercise, I find it wasn't the disks, because the disks are operating asynchronously. So this was a case where it actually was the disks. Different methodology. This actually has a smaller audience because it requires more expertise and it requires more time. So to summarize that example, what happened? The customer, the first and second level support, spent a lot of time chasing down network packet drops. What could have happened, what should have happened, the customer or first level can follow the use method and quickly discover potential memory and disk issues. Memory is fixable by customer reconfig. In fact, the customer may not, we may not even needed to have used microstate accounting or dynamic tracing to prove the memory issue. If you're out of memory in your paging, you should just fix that. And so that would have actually saved our time if they'd found that earlier. Disk, you probably do want to confirm it because it is so often asynchronous. You don't just want to trust what ISTAT tells you. And so that's where you do often want to use dynamic tracing of the file system. And so that could have gone to first or second level support. This is fast resolution. It frees everyone's time. So everyone isn't aimed in the wrong direction. I never found out whether there was a legitimate packet drop issue. I never saw it when I was tracing. I found other issues and I proved using latency analysis that they were hurting the application. It's very possible that the customer was right and that there is a third issue, which is network packet drops, which was hurting the latency. I don't actually think so because I was watching retransmits at the same time I knew that there was an issue and they didn't correlate. But it's a possibility that there's still an issue there somewhere. Performance issues often happen in multiples. And so you need a way to keep looking when you've found one so that you find them all. And then you can rank them and solve them. So what this talk is about is performance methodology. And this is really interesting for me. I have not given a talk like this before. Usually I'm talking about tools, products, books. This is not a tool. It's not a piece of software you can download. This is not a product that anyone is selling. This is documentation. This is a procedure that I can include in my slide deck, that I've written a blog post about, and it's something simple that you can learn. That's not to say it can't be a tool. It can be a tool. You can write a tool to support this methodology. People who are creating monitoring solutions can provide guidance to follow a methodology in the monitoring solution, or at least the metrics that you need, the information that you need. Why methodologies now? So, performance analysis in the past, circa 90s, was metric, being a generalization, and I know that there are exceptions, was generally metric oriented. That is where the vendor creates metrics and then performance tools to show you the metrics, and users develop methods to interpret them. A methodology that was commonly followed, which I call the tools method, involved listing the available performance tools that the vendor gave you, then for each tool, list the useful metrics, and then for each metric, determine the interpretation. And so you can build your own checklist that your staff follow. Listing available performance tools, that might be VMstat, MPstat, ISstat, SAR, TOP, those type of tools, NetStat. Listing the useful metrics for VMstat, I might want to look at scan rate. And then for each metric, I might come up with a rule for interpretation. If scan rate is non-zero for more than 5 seconds, the system is really out of memory, and you should work on that issue. This is largely effective, and if you asked me before dynamic tracing existed, I would have said, this is state of the art, this is how we do it. And I've solved a lot of issues using this approach. This approach works. It is actually problematic. Vendors often do not provide the best metrics. This is something that is counterintuitive, and it's always the counterintuitive issues that make life difficult for us. When you look at the vendor documentation, it's very formal and final and polished. You think that the tools that they're telling you to use, the VMstats and SARs, these must be the best tools that I can use to work on my issues. So I worked at a vendor at Sun Microsystems, and I created new features. I created the development for the ZFS L2 ARC. And what happened with me, just as a case study, I added metrics in there so that I could see my own code working. So I could debug it and have some idea of performance. Sometime later, someone from the performance group emails me and says they've created a tool based on my metrics. And that tool is now being used by customers. It's called ArcStat. What never happened was we never had a meeting and said, what is the best metrics to give to customers? That didn't happen. And I actually asked around, like, does this happen? Is there a way to do this? In that case, it wasn't so bad because I have a lot of performance experience, and so I did actually add metrics that were useful. The guy who wrote the tool also is a performance expert, and he did actually come up with a very useful tool. So in that case, it actually worked out, and we both probably assumed each other knew what we were doing. But there are other cases where the kernel engineer and the tool developer haven't discussed thoroughly what is actually best for the customer. And so don't assume that what you get from the operating system is best. It may not be. You may need to create your own. Especially if there are areas that are not instrumented at all. And you can be blind to issue types. So why now? What has changed from the era of the tools method of just following the tools that you're given? What changed is nowadays we have a lot of open source. And so for a lot of the applications I'm looking, I started off doing Solaris performance and then saw the transition where this was open Solaris, and I could read the source code to what I was analyzing. And that was hugely beneficial. It helped me understand performance much better, and the source code is often the best documentation for what the metrics mean. I can look at the code path to where they're incremented. The other thing that happened was dynamic tracing. So hands up if you've used dynamic tracing in some form, like dtrace or perf events, the dynamic tracing part. So about 2 people, or system tab, 3 people. Dynamic tracing is fantastic. As a performance expert, this is the best thing that's happened for me in my career. Although at the time I was really annoyed because I had in some ways reached the top of learning what I thought would be everything about performance. And then dynamic tracing was created and the mountain became much higher. There's so much more we can do. So my workload increased because I can now solve many more issues that previously I didn't have to solve. I didn't have to solve because there was no way to solve them. So I now do much more work. But it's exciting. Dynamic tracing is where I can take the source code, I can look at the source code to an application because it's open source, and I can say, let's instrument these functions, or subroutines, or whatever they are. Give me nanosecond timestamps for when they enter and return. I don't have to restart anything. That's why it's dynamic. So this is great. Customers often tell me, my database is performing badly. Did they start the database with various extra debug modes or the perf events log enabled or things like that? No. Can they restart the database to do that? Well, you have a couple of minutes of downtime, and then it takes 2 hours for the database cache to warm up. And the customers don't like that. And it actually creates, it's creating more of a problem for them. With dynamic tracing, I can instrument the database immediately without restarting it. And sometimes I can have the problem solved in less than 5 minutes. So, source code plus dynamic tracing, I can solve performance of anything. I can show where latency originates from anywhere. It's only practical in open source software. The hardest part, however, given this amazing superpower to actually answer anything, is knowing what questions to ask. You can learn dynamic tracing, you can learn the syntax for dtrace very quickly. You could learn that, if you're a programmer, you'd learn that in a day or 2. But knowing how to actually use it, it depends on your performance background. If you don't performance a lot, it would be obvious, you could use it straight away. But for beginners, you need a starting point. And given those changes now that we're so open source focused and we have dynamic tracing, now performance analysis is question orientated, where you can begin with the questions, users pose questions. You can check if the vendor has provided metrics to answer those questions. If they have, that's great. You don't have to do any more work, you have the answers. If not, you can develop custom metrics using dynamic tracing. And to answer the issue of, but what questions do I ask of the system? You can follow methodologies, and the methodologies give you those questions to ask. So given this superpower, this is why we can do this is why I'm now spending a lot of time developing new methodologies that I can share. This is just a documentation I can put in the slide deck, because we have the power to do this. If I did this in the 90s, it would just be an academic exercise. That it wouldn't actually help anyone. Because I would be talking about viewing performance of all sorts of areas that were black boxes that you can't look inside. So why bother? With dynamic tracing and open source, I now can look inside all of those black boxes. So I can develop new performance methodologies that can be really beneficial, and people can actually use it to solve problems. So this is why this is happening now, is that we have this ability. The audience, as I've just mentioned briefly, for methodologies, this isn't just for beginners, it's also for experts. For beginners, this provides a starting point. One of the most difficult things about performance is knowing where to start. Performance is complicated. For experts, this provides a checklist or a reminder. I'm human, I forget things, but with a methodology, I can make sure I don't forget something important. I can follow that checklist. I'm going to go through 4 methodologies, and I'm going to focus on the use method, but I'll go through the other ones briefly. By listing them here, I can emphasize that the use method is only one out of many. You can have a virtual toolbox of methodologies. It also shows where the use method is used by you, the end user. It's used fairly early on. It's not the first thing you would do, but it would probably be the second thing. And then there are other methodologies that follow on. The first thing is the problem statement. And this isn't actually new, but I've just included it for completion. This is what staff often go through. What makes you think there is a performance problem? It's the first question you should always ask. Has this system ever performed well? I've been given performance tickets where the customer says, there's a performance problem, please solve it. And so you're having a look and you're saying, oh, what changed? Did they run out of memory? And did the disk file system fill up? And that's starting to be slow? Nothing changed. The system has always been slow since it was ever deployed. And so I'm trying to find a change, and there is none. And so this is why I need to remember to ask this early on. Did it ever perform well? Am I looking for a change? Or is it looking at the current performance that it's always had? If it did change, does the customer know of the change? Did they upgrade the software version? Did hardware change? Did they suddenly have a whole heap of new users? Did they announce some great feature on Twitter, and now they have people around the world accessing their service? Were they just on Hacker News, or Slashdot, or Reddit, or one of the other websites? Can the performance degradation be expressed in terms of latency or runtime? Those are the most important metrics if you're coming from the application level down. Does the performance affect other people or applications? And general stuff about the environment I'd include in this checklist as well. What software and hardware is used, what versions and configurations. Sometimes I can solve performance issues straight off step 6. You look at the load you know they're applying and the system they've configured, and you think, wow, you should not be using double parity RAID over 6 disks for this type of workload. It's just not going to work. It shouldn't have worked properly. It's just not configured well to begin with. But it's important to know that early rather than later. So having gone through all this latency investigation, and then you realize, wait a minute, they've configured what? So I check that early. After that first quick rundown, then you come to use method. And it's actually pretty simple. It is a quick system health check. This does not find every issue, but it finds many issues. So this is why this is a tool in your methodology toolbox. For every resource, you check utilization, saturation, and errors. Utilization can be the time a resource was busy, servicing work, or it can be the degree that a resource was used. Saturation can be measured as the degree of queued extra work, and errors are any errors that the device gives. I've drawn a little picture to kind of the grey box is a device to show where those metrics originate. This looks a bit like queuing theory. That's fine. If that helps you understand it, that's fine with me. To go through the sort of resources you should be looking at all the hardware resources. All the hardware resources in the data path. That includes CPUs at the socket level for cores, for hardware threads, main memory, network interfaces, storage devices, controllers. This is where you need to understand how the system has been built, and then all the interconnects. These could all pose performance bottlenecks. It can be kind of hard to know exactly everything that exists. A great way to determine that is if you have functional diagrams. And if you talk to server vendors, The hardware teams often have these in amazing detail, especially the people who build the servers and build the physical chassis. If you can find those diagrams, you can definitely see everything. I've had the blueprints down to the pinouts of how these get built. They're fantastic. I really love it because I can see everything that is being used. And what you're trying to do is you're trying to analyze every component in the data path for your workload. So some of the functional diagrams might include things like the power LED. Don't need to look at the performance of that. You do need to look at the performance of everything, everywhere your data goes. I've drawn a generic example, which will be different to what you've got. This is the sort of thing I would expect to see for, say, a 2-socket server, where I have a memory bus on each CPU socket. This could be architected differently. I have a CPU interconnect, which will connect. Here, I only had space for 2 CPUs, but you could imagine many more. An I/O bridge, which will be a chip on the system board, which connects an I/O bus directly from the CPU, which is one of the high bandwidth ports, to the expanded interconnect, and that can be things like PCI. And then on the expanded interconnect, that's where you have your I/O controllers, like your host bus adapters, your network controllers, and all the other expanded cards plugged in. And they themselves have interface transports. So your I/O controller may have SAS or SATA, your network controller may have Ethernet or InfiniBand. This diagram is fantastic because it can serve as a checklist of all the components that I need to examine. Even if you don't know how, even if you don't examine it, knowing that you have not examined it is very useful. This is bringing unknown unknowns to be known unknowns. And it is valuable to understand what have I not checked. So if you really have a really important problem, and you know you've never ever checked the CPU interconnect, I've never ever checked that. Maybe for that really important problem, that's the time you should learn how and go and do that. Now on that diagram, there are different resource types. And so there are I/O resources, like network interfaces. Utilization is the time the resource was busy. Other metrics can sometimes work, like current I/O per second over the maximum possible, or current throughput over the maximum possible. I say sometimes work, they get tricky, because different I/O can take different amounts of time to service. And so IOPS can often be a poor metric to use. Sometimes it works. Current throughput on max, for network interfaces that probably works. Usually works. For capacity resources like main memory, utilization is the space consumed. Some devices, like storage devices, act as both resource types. So a storage device serves IOPS and can be busy for a certain amount of time. And storage devices are used to store things, so that's where you'd store your file system or your swap device or whatever. And in terms of performance, it's also a useful, simple thing to check is how full are those devices, how full is the file system. You can also look at software resources, things like mutex locks, thread pools. A thread pool is where your application may have a fixed pool of threads to serve as work, say 10 threads. Can you easily check how many of them are busy? Are they all busy, or only one of them busy? Are they saturated with work? Is more work coming in than that pool can deliver? Process or thread capacity, there may be fixed limits on the system. File descriptor capacity, there may be fixed limits on the system there as well. And there could be other things that are in some ways a fixed software resource for your application. You can use a similar quick checklist to see if there's any issues worth investigating. As a flow diagram for the use method, I'd actually begin by checking errors. So begin with start with each resource and then check if it has errors. Why errors? Errors are often the easiest thing to interpret, and so it's quick to get them off the table early. because any non-zero error is a potential issue worth investigating. Utilization requires more interpretation. You can have devices that utilize that aren't really a performance issue. And then comes saturation, whether it has more work than it can deliver. I could go through many more anecdotes where I've a similar situation, like my example, where it's been through all the support tiers and they haven't been able to find an issue. And I've just looked at the resource errors and found, oh, the system disks have errors. They're actually bad disks. And there's lots and lots of soft errors and some hard errors. It's actually causing a performance issue. Very simple to check. No one's checked it. No one's followed a methodology. People have assumed the issue is somewhere else. To give you interpretation of utilization, 100% is usually a bottleneck. It can be a bit confusing for things like storage controllers that can accept more work, even though they're busy all of the time. 70+% is often a bottleneck for I/O resources, especially when high priority work can't interrupt lower priority work, such as disk devices. And you're just more likely to queue behind work once it starts to get quite busy. And it doesn't matter whether it's 70% or 60% or 80% what you use there. Beware of time intervals, however. 60% utilized over 5 minutes may mean that you've been utilizing for 100% for 3 minutes and then idle for 2 minutes. You want to measure these as 1 second intervals if possible. And at some point we may have investigated this a little, going down to the 100 millisecond mark to look at utilization. It's best to examine per device so that you can identify unbalanced workloads, where a single device is maxed out. And that's something that averages can hide. So I really don't want to look at average device utilization across the board. Saturation, that's easy. Any non-zero value adds latency because you're queuing, and errors should be obvious when things have gone wrong. To go through some combinations, so easy combinations, I've just done some of them here, so CPU utilization, CPU saturation. Think about how you would measure this on your system. Can you measure CPU utilization? Generally pretty simple. CPU saturation, when there's more work than the CPUs can deliver. What about things like storage device saturation, or memory saturation? These are very commonly analyzed, so CPU utilization is CPU utilization. CPU saturation is the run queue length or the dispatch queue length, where you have more threads or tasks that can run than you have CPUs, and so they're queued. Memory utilization for the available memory, or saturation if you're paging or swapping, and so on. Those are the easy ones. Some harder ones would include things like CPU errors, network saturation, storage controller utilization, CPU interconnect utilization. Does anyone in the room measure these? So there's no hands up. That's fine, that's why we have methodologies. And these have serve as checklists and reminders so that we can go and start to look at these. So, as examples, when this starts to get tricky, that's why I said harder. CPU errors can be correctable CPU cache ECC errors. That's an example. I had one of these whilst I was performance benchmarking a system, and I was watching the throughput line when it stepped down by about 10% and kept going. And it's like, oh, what just happened? And so I stupidly did not follow my own methodology and looked at everything for an hour before I decided to use the user method. It's like, I'm just going to check everything. And I found out that one of the CPUs had too many ECC correctable errors. So that they had been corrected, but this was a Solaris system that was using FMA, and it automatically offlined that CPU. This is predictive self-healing. And so I actually had a CPU die, or was detected to be about to die during a benchmark, and all that happened for me was the throughput stepped down by 10%, which I guess is a testament to that particular software feature. But I wasn't expecting that, so I spent a long time looking elsewhere. That was a CPU failure. Network saturation, it depends on your device driver. You may have a metric called no-can puts, which is when its buffer is full and it can no longer accept work. It's an example of a saturation. Storage controller, for those things, you may be better off with the IOPS over the known max or throughput over the known max, because in terms of device busy, when it's fronting many back-end devices, that becomes less useful. CPU, the interconnects, you can look at the ports from the CPUs that talk to the interconnects. For CPU utilization, it can be per port throughput over max, bandwidth, and memory interconnect, memory store cycles. And IO interconnect saturation, bus throughput on max bandwidth. So, more difficult metrics. To be thorough, to actually explore these, you'll need to use tools like CPU performance counters. These come under many different names. They can look at the bus and interconnect activity. And for example, on Linux systems, there's something called Linux performance events, LPE, or perf events, and you can look at them. On the illumos-based systems I work with a lot now, we use CPU stat. dtrace actually has visibility into those CPU performance counters as well. And for dynamic tracing, that's often used for saturation and error metrics. Both can get tricky. Tools can be developed to help. I often see new variants of things like top being produced. There's many different versions of top nowadays if you're on a system. Which is great. People are improving upon the tools that we use, but they aren't solving the unknown unknowns, the things, for me it's the known unknowns that I need to know bus utilization. I need an easier to use tool for that. So I would like to stop seeing top variants for processes or tasks. I would like to see top variants for the interconnects and for the buses. I've written dozens of these and released them open source for CPC and dtrace. But there is much more that can be done. It'd be great if people in the audience, if you're interested in that, there's many. If you follow the methodologies, you'll see the questions that need to be answered. Just to go through a couple of other methodologies very quickly, because for completion, to show where the use method fits. There is workload characterization that I use a lot to solve issues. And it's because the best performance wins are from eliminating unnecessary work. And you can identify that if you look at who is causing the load, process ID, user ID, IP address. Why is the load called, the code path that was calling it, and what that's doing. What is the load? Just characterize it. How many IOPS is it? Is it reads or writes? What's its throughput? What's its type of operations that it's doing to the database? And then how is the load changing over time? Is it changing by minute, hour, day, or week? Very basic questions, worth examining as part of workload characterization, because you often say, the system's doing something dumb. The workload applied is dumb. I can eliminate that. Someone left this backup task running that we don't need anymore. We can turn it off. Drill down analysis is the last methodology that I have in this deck. This is where you get serious about getting right down to the source of an issue. It's like peeling away software layers to drill down. And I've got an example of a software I/O stack where you may start the application, go to the system call interface file system, and then deep into the kernel. And you can do this with open source and dynamic tracing. This is going back to the why things have changed and why we can do more of these methodologies now. For example, here's just a almost random lump of code from ZFS, or ZFS. This is the arc checksum equal. I did analyze this previously for performance, so it rang a bell when I was looking for an example. To do latency analysis, what I might do is I might look at the latency I might use a strategy of pairs. I might look at the latency from A to B, and then the latency from C to D. That's very easy to do with dynamic tracing. I can see the source code, I can then use dynamic tracing to look at the function entry and return nanosecond timestamps, and then compare it. And if the latency is in that Fletcher2 native function, which does the checksum, that's pretty much equals the A to B latency I've identified. There's other ways you can do it. You can do binary search of latency as well. That's fine. But it does need to be open source. Otherwise, it's just guesswork. And if it is proprietary and closed source, which I don't like working on at all, you may find that the license agreement prohibits you from delving into it in this much detail. Well, hopefully not, but other methodologies to mention, so there is something called Method R that was developed a while ago for Oracle databases. Even if you're not on Oracle databases, it's an interesting methodology to study. I didn't talk about experimental approaches at all, but they can be useful as well. And that's where you perform a known experiment to investigate latency or throughput or whatever. So the last section was, this talk was about methodology, but I did want to show you some of the tools that these direct you to. So for illumos-based operating systems, I have got a blog post. It doesn't fit in the slides because it would be more than a dozen slides. But if you go to this blog post and I go through all of the different tools that can be used for those metrics. So CPU utilization, things like MPStat, VMstat, PRstat, lockstat, dtrace, CPU saturation, more dtrace, and so on and so on and so on. And so this is the end result of the use method, is where you come up with your own very detailed checklist that's comprehensive. You're checking all of those hardware and key software resources. And it can also be followed by the first level support. It can be followed by customers. And so you can find performance issues more quickly. It's very prescriptive. And I've got a website where I go through the Linux version, but I'm still updating as I'm finding slightly better ways to do things. So CPU utilization using the MPStats and SARs and PS. CPU saturation going into VMstat, /proc, perf shed latency. It's actually a pretty neat tool. Dynamic tracing, which can be system tap. There's also 2 ports of dtrace for Linux that are coming along very well and answer all of these questions as well. And CPU errors, this is where you're getting down to the CPU performance counters or CPU counters level, and you're using things like Linux performance events to look at counters like the single bit ECC errors recorded. And if you do that, there's manuals from the vendors. Has anyone used, I did ask about dynamic tracing, but has anyone used the CPC or LPE, the CPU counter style analysis in the room, where you're looking at? It is actually really complicated. And this is why I mentioned it would be great to have more open source tools built upon making it easier. There was something called PAPI released, which provides a generic interface for accessing them, because it did differ per vendor. And I have taken a swing at writing tools myself to make it easier to investigate your bus utilizations and other things from that level. The last thing is products. Earlier I said some methodologies could be supported by monitoring solutions. I work at Giant and we develop cloud analytics, and so we make sure that things like utilization are presented very easily. This particular screenshot shows a heat map of CPU utilization across a live cloud. It's updated in real time. The y-axis is utilization up to 100%. The x-axis is time, and the color depth shows how many systems on the cloud were at that utilization and time range. And the darker it is, the more there are. And there's actually a fourth dimension here where we use color hue so that we can then get more information about those pixels. And so I've clicked on the top line, I did blur it out. I clicked on the top line and it immediately tells me which system on the cloud has that CPU that's running at 100%. Most of the CPUs are down here. So most of the CPUs are near idle, a lot of headroom, but there is some CPUs at the top. And so I can click on them and go straight to them. And we have similar things for investigating saturation and errors to support the use method. In the future, there may be more methodologies for advanced performance issues. I did a lot of work on KVM recently, and we solved some network performance issues. It was interesting because that was mentioned in the previous talk. Just to mention it, I did not find, there was one issue I worked on for bandwidth, there was no real good methodology for. So I think this may be a place to innovate and come up with a better methodology for bandwidth analysis. It was actually a very difficult problem. Innovative methods based on open source and dynamic tracing I've mentioned, less performance mystery and guesswork, better use of resources, price performance, and it's easier for beginners to get started. You have something to follow. And those are some resources of a lot of the things I've got on my blog, dtrace.org/blog/Bruno. So thank you for attending, and are there any questions?
Hello. In a virtualization environment, how do you apply the use method where you cannot isolate one virtual machine from another?
Okay, so you mentioned in a virtual, it was a virtualized environment. So virtualized environment is what I actually do a lot of. And people are really worried about multi-tenant effects. And utilization, often for the tenants, is not utilization of the entire system, but it's utilization of that virtualized instance, the resources that it's been delivered. And so, for example, for CPUs, a virtualized tenant may have fixed virtualized CPUs, which is what some technologies do. We generally like to use operating system virtualization, which allows you to burst across many CPUs. But it's important to help customers still have some means of doing utilization checks. And so we've added metrics to the system so that you can see basically how utilized you are of that virtual resource. So it is a problem that we've had to add metrics to help people understand. But there's basically two layers. You've got the host-based utilization, which is usually studied more by the operators who are running the cloud. And then within the tenants, you have the utilization of your tenant resources. And if there are caps, if there are throttles, we've done a lot of that. We've added throttles to ZFS for the file system. We have CPU caps in SmartOS. So visibility of each of them, so you can see if you've got utilization or saturation states. Something else to mention is you actually do need, if you're on a vendor solution virtualization and you're using the file system or something and there is no sort of utilization metrics, it may be because they don't have a means to throttle, and each tenant can be at war with each other where they're using the resources. And as an end user, as a tenant, when you're looking at that device, you don't know if another tenant is utilizing it. You don't know if it's you or not. So that's where it's much easier if there is a technology that's been added to throttle it and to provide you with more statistics. Otherwise, you use other techniques for debugging. Like in that particular situation, I would use dynamic tracing of the file system interface to find out what workload am I applying to the file system. I can see what the disks are doing, but there's this virtualization stuff in between. So yeah, to recap, the methodology does work for virtualization, but you're looking at the utilization of your allocated resource. And you have to be constantly aware that many of the system tools are going to tell you about the whole system, not just your tenant, which can be very confusing.
I just want to understand, how do you really use the dtrace to show that piece of code? What methodology do you use to know that you have to look at that piece of code? How did you get there?
So for dtrace, doing the drill down analysis, there are two ways to go about doing it, and I could do a whole presentation on it, and I should do a presentation on some point. It's either top-down or bottom-up. So I'm either going to start from the application, and then I'm going to look at what that application request is doing, what calls is it making, say, to the operating system via syscalls, and then from the syscall level, which one is the slow one, and then what does it call lower down, and it's a lot of looking at the source code and how what they then call. The other approach is going bottom up if it is So that particular piece was for CPU and was doing the Fletcher checksum in ZFS. Going from the bottom of the stack up is when you start with the resources. That can often be easier because I can use stack backtraces basically to give me the navigation route through the kernel. So I can profile the CPU and then look at why was the CPU busy? Look at the ancestry through the stack backtrace. That's actually how I would have found it. That's actually how I did find that one. Was I was able to use profiling to get a coarse idea that this was hot, and then I used the latency analysis to prove it, where I'm looking at the actual breakdowns. But just to summarize it briefly, it's either top-down, which is tricky and you're going through a lot of code, but sometimes you get lucky and you go up from the devices and you look at just the stack backtraces. How was I calling this guy out? How was I profiling who's using the CPU? There are lots of examples on my blog. If you look at flame graphs, they make the CPU analysis very easy. Thank you for attending.